Welcome to the Azure Machine Learning course. Today I'm going to talk about using Azure Machine Learning. Again, this is hands-on, so if you got your Azure Pass and you have an account, I invite you to log into studio.azureml.net, right? That'll take you to the Azure Studio and sort of just log in and we'll we're going to be running things from the Azure Studio pretty soon. What I want to talk about today is, can we lower the volume just a little? Thank you. What I want to talk about today, down. Thank you. So what I want to talk about today is really focused more on maybe the mechanics of doing machine learning, right? How do we do machine learning? And less focus on why we do it this way or this other way. There are some things in the mechanics that I will explain, but I'm doing another session tomorrow on how to choose a machine learning algorithm, right? And that's going to be more focused on the whys. Today, we're more interested on the how, right? So with that said, we're going to try to spend a lot of time in the studio just familiarizing ourselves with the Azure Machine Learning Studio. This is a great environment if you don't know R or Python, if you want to experience machine learning in a really very powerful sort of way without necessarily having to do too much coding, right? So this is the agenda for the day. Oops. We're gonna start by just running some examples in Azure ML. Right? We just want to get our hands dirty with using Azure ML. It's an environment that takes some getting used to. It's a little bit strange the first time we work in it. We have to get used to just dragging and dropping a bunch of things and knowing where to look and how to connect things together, right? So that's going to be the first thing we do is just let's log into Azure ML and let's try to work out an example. Then we're going to focus on some of the basics of machine learning, right? What are some important things that we do when we do machine learning, things to pay attention to? We're going to spend more time on some of the concepts behind machine learning, right? So I said we don't spend too much time today on the whys, but in the concepts part, we will talk about some of the whys, some of the important things. And then we'll finish, if we have time, we'll finish by talking a little bit about deployment, which is something that is really easy to do inside of Azure ML. Okay. So here's a lab, right? Probably weren't ready for this, right? The first slide is a lab. And so just go ahead and log into the studio. And I'm going to give you maybe just 2 minutes. See if you can get it done by yourself. The easiest way to learn Azure ML is to try it yourself, make mistakes, just struggle and kind of get used to the environment. So I'll give you just 2 minutes to see if you can do this, and then we can do it together. Again, I invite you to work with your neighbor, just whatever you can do to help each other out. And just take a moment to do this. And if you don't figure it out, no worries. We're going to do it together in just a minute. Okay, so I wanted to just give you a moment to become familiar with the environment, see if you can find things I think personally that the environment is very intuitive. Once you get a hang of where everything is, it's really not difficult to kind of know where to go next, right? But I just wanted to give you a chance to do it on your own, right? I was hearing a lot of clicks, right? That's a good thing. It means you're active. It could also mean you're all playing video games. I hope it's not the latter. So based on the clicks, I would say things are going well, right? Let me log into Azure ML. It's okay if you didn't finish it. We're going to redo it. Right? And let me just familiarize you with just the basics for now. So this is Azure ML, right? And I'm looking at my experiments. If you logged in for the first time, you probably just have one experiment right now. I have many experiments here set up. There's other things that we can do. We have a place where we can look at any data that we brought into Azure ML. Some data is already in Azure ML that we can play with, and we can also bring in our own data. We have notebooks. So if you've heard of Jupyter notebooks, you know, I know it was mentioned a couple of times by some of my colleagues. So Azure ML gives us an interface for launching a Jupyter notebook if we wanted to. This is attractive if you don't want to use the Azure ML Studio. You want to just write your own R code or your own Python code. But in our case, we're not going to be using a notebook. Right? And then we have our experiments and some other things that we don't really need to get into right now. But this is the big one. Every data science project in Azure ML can be described as an experiment. Right? So we're going to start with some data. We're going to clean that data. We're going to run some operations on the data. Then we're going to experiment with different models. We're going to try different models. And the model is going to use the data, build a model, run some predictions. All of that is called an experiment. So here's a new button. Right? To start a new experiment, we can start from scratch, and that's what the blank experiment is for. So if you click on that, you would get basically a blank canvas with nothing in it. We can see that there are some options on the left side. They include ways that we can bring in data. So there is a data input option, right? And I can drag in the import data. And with import data, I can see that when I drag it in and drop it, when I click on it, it's outlined in blue. This is how you know you've selected a particular module. This box, by the way, is what we call a module. Okay, so I'm going to be referring to different modules. And right now, we're looking at the import data module. Another thing that happens is if I click on the canvas, notice on the right side, nothing is showing. As soon as I click on a particular module, some properties show up. And so I notice that for import data, I have the option of choosing between a Hive query, an Azure SQL database, an Azure table, blob storage, and all of these different options that are available to me. Right? So import data is how we can go and query various data sources and bring them into Azure ML for a machine learning experiment. Right? Anyway, for now, I'm going to ignore this. I'm going to go back to clicking on new, right? Because in addition to starting a blank experiment, there are also a bunch of sample experiments set up for us. This is a great way to learn. We can choose one of these experiments, we can open it up, and we can try to understand what it's doing and examine the different pieces of it. Right? And what I'm going to do is search for credit. And I see that there is an experiment called binary classification credit risk prediction. I'm going to open this in the studio. So it takes just a few seconds or so to load up. So I'll just give it a minute, and pretty soon you should start seeing the different modules, how they're connected to each other, and sort of where we start, which is usually some form of data, and where we kind of go with the experiment as we try more and more things with it. Okay, so there's my experiment. I guess I just had to scroll down a little bit. Right? And there's a lot of things going on. Right? So this might look pretty confusing. I'm hoping that at the end of today, when we finish, a lot of these pieces that look confusing right now are going to start making more sense. Even if they're confusing, we can kind of start at the top, and we can just try to read the modules to guess what is going on. Right? So we have some data set there, and it looks like we do something to change the metadata. Right? So that could be the column names, that could be something with the column types, and so on. Then, for some reason, we split the data, so we'll talk about why we do this. Right? Then we run some R scripts. Right? So it looks like in Azure ML, we have the option of running R scripts. That's kind of a useful thing to know about. The same is true of Python. Right? Then from there, we run some data processing. In this case, the module is called normalize data. Like normalization is one form of data processing, and we'll talk more about that maybe tomorrow when we talk about choosing machine learning models. Then we can see the names of some common models. Here's a model called 2-class support vector machine. Right? It's a machine learning predictive model. And we can see that we're building models. That's also called training. We're predicting with models, which is also called scoring. So the word training and scoring are very commonly used in machine learning. Training is the process of building a model. Scoring is the process of making predictions with a model. And then we evaluate models. Right? We want to see if the models are good, right? and so on. So there's a lot of different pieces to this. But what I'm going to do is I'm going to zoom out. And I'm going to keep the first and the second module, and everything else I'm going to get rid of. Right? So I can select all of that, and I can press delete, and I'm left with basically just those two. Okay, so let me just go back to, they disappeared again. Where did they go? There. So let me just go back and actually run this experiment. Right? So you can click on the run button, and it's going to start running the individual modules in the order that they're connected to each other. And when we finish running them, we can go here and we can do a right click on edit metadata and results data set and click on visualize. And what this is going to do is if the module does something with the data, we can look at it. Right? So let's go back to the original data, German credit data. It's a data that already exists in Azure ML. If you go to data sets and try to visualize it, you would notice that the columns in the data, there are 21 columns in the data and 1,000 rows, and the columns are just called call 1, call 2, call 3, and so on. So we come here to edit metadata, you click on that, and you can see that we've selected a bunch of columns. If you scroll down, you would see that we're providing new column names for the columns in the data. Right? So edit metadata in this case is just renaming the columns in the data. So if we do a right click on edit metadata and go to visualize, we can now visualize the same data, but instead of call 1, call 2, and so on, we can see the actual column names showing up in the data. Okay. What's interesting about the data is we can click on any of the columns. Notice that we see a distribution, a histogram, or a bar plot in this case. Right? If it's a numeric column, such as duration in months, we would call this little visualization there a histogram. If it's a categorical column, such as this one, personal status and sex, then we would call that a bar plot. right? But it's a visualization of the data. We can pick something like property, right? It's not very descriptive. It's using codes A123, A121, A122, and A124, right? So these are probably common industry codes, and they exist in the data set. We don't really understand what they are. We can go to the data dictionary to try to understand what those represent, but we can at least see that A123 is the most common category for this column, and the rest of them are pretty well represented as well. Some of the columns, like number of people being liable to provide maintenance for, right? We have one category that's very highly represented, another category that's not very common. And the last column in the data is the one that we're interested in, right? In machine learning, we call this a target. That's the column that is going to be our column of interest. We're going to build models that are going to try to predict this column. Right? So future data coming in, we want to be able to predict if they're a credit risk or not. And for the historical data that we have, the one that we're looking at here, we know if they're credit risk or not based on the values of this column. So this is Azure ML. It's not the end of the story. We're going to do more with this, right? But we started with a little experiment, and we made it so that we have a data module and an edit metadata module, and the edit metadata was just renaming columns in the data. The next thing we're going to do with this is we're going to go and look for a new module called summarize data. Right? So we looked at some summaries of the data when we visualized the data and edit metadata. Right? But we're going to get more. Right? So all of the modules are shown here. Summarize data. Right? So you can type that in the search box, and you can see there is a module called summarize data. I'm going to drag and drop it in here. Probably need to. It doesn't like me zooming in, zooming out. So I'm just going to put it like this, and I'm going to connect what comes out of edit metadata to summarize data. And now I'm going to run this again. So there is some amount of efficiency going on, right? The first time we edit the metadata, it's going to rename the columns. The second time, it's not going to do anything. It's already done it, so it's just going to notice that summarize data is the one that didn't run, and it's going to run that module. Okay. So we can go back now. Here's summarize data, and I'm just going to look at result data sets, visualize. Okay. And summarize data did this for me. It took all of the columns in the data, it put them inside of these rows, right? So each row here is one of the columns in the data. And then for each row, it's providing me with some summary statistics. I can see the count, I can see the number of unique values, I can see if there are any missing values in the data. For when the data is numeric, I can see minimums and maximums. When it's not numeric, that's not relevant. Same thing with averages, mean deviation, first quartile, median, third quartile, and so on. So these are all statistical summaries that are relevant to numeric data only. I can also see the original distributions, so those histograms. If you hold it on a particular column, you can see more information shown here on the side. Right? So there is a lot of information in here. Some of it is only relevant to numeric data. Some of it is relevant to both numeric and categorical data. And we can basically get a good sense of what sort of data we have by running summarized data. So that's it. That's our first little experiment. We were able to take some data, bring it into Azure ML, and we were able to run some summary statistics on it. And we can now examine the data and have a good sense of the data. If you come to the session tomorrow that talks about how we choose a machine learning algorithm, we're going to talk more about how it's extremely important for us to spend some time examining the data. Right? In machine learning, we often say garbage in, garbage out, meaning that if your data has problems and you use that data and pass it to a machine learning algorithm, the model that you build is not going to be a very good model. Right? It's going to provide you with bad predictions, for example. Okay, so let's learn some basics of like how we do machine learning. Right? This is what we're going to learn in the next set of slides. We're going to learn that machine learning algorithms are divided into supervised and unsupervised learning algorithms. We're going to see what the difference is. We're going to look at some examples of each, and we're going to see how we can evaluate supervised learning algorithms. All right, so let me just make this big. All right, so what is machine learning? Right, first of all, it's some kind of algorithm, but an algorithm is not enough, right? There are lots of algorithms that are not machine learning algorithms. What makes machine learning a very specific kind of algorithm is the fact that it uses data, right? So we have data, and we have an algorithm that knows how to learn from data. What we mean by learning is that it's going to try to understand the data. It's going to give us a set of rules. Right? Most of the time, those rules have to do with here's how you can predict credit risk using all these set of other inputs. Right? It's one example. It's not the only one, but most of the time, it's something to do with prediction. Right? So this means in machine learning, we don't want to be explicit. Right? We don't want to say, if you want to predict somebody's credit risk, here is what you need to look at, then you look at this other thing, then you look at this thing. No, we don't want to have to do that. We want to just give the algorithm some data, say, this is what we know about people. Now, can you go and figure out what the rules are for predicting credit risk? Okay. So sometimes, like the case of the German credit data that we were looking at, we already know the answer, right? We have historical data, and our historical data is going to tell us here is somebody who was a credit risk, and here is somebody who was not a credit risk. Right? In this case, credit risk is a categorical output. We're trying to predict if someone is yes or no a credit risk, and so we call that a classification model. And when we know the answer to what we're trying to predict, we have what's called supervised learning. Right? That means that we can build a model. Our model is going to make predictions, and we can evaluate our predictions because we know what the answer really was. If somebody was a true credit risk and the model predicted that they would be a credit risk, that's a good thing. If somebody was a credit risk and the model says they're not a credit risk, or vice versa, that's a model that's making that's an error in our prediction. Right? So in supervised learning, we know the answer to what we're trying to predict, and so when we build models, we can evaluate them. Unsupervised learning is a slightly different situation. We don't really know any answers ahead of time. Right? We're going to see that the most common case of unsupervised learning is something like clustering. If you've ever built something like a bunch of clusters, you don't really know how many clusters there are. You don't really know if the clusters you have are good or not. There is no way for us to really evaluate things, right? We can sometimes go by some business logic. We can sometimes kind of build clusters and see if they're good based on how well the business is responding to them. But right off the bat, it's very difficult to know if we have a good model or not. Right? So those are things that fall into the category of unsupervised learning. Okay, so supervised learning is mainly comprised of regression and classification. Regression means we're trying to predict a number. Right? If you're trying to predict somebody's income, that's a regression problem. Classification means you're trying to predict a category. If you're trying to predict if someone is high risk or low risk, if someone is a credit risk or not a credit risk, that's a classification problem. Clustering is an example of unsupervised learning, right? And we'll get a better sense of that a little bit later. So here's a visualization that kind of shows all three of them. So the two plots, or the two visuals on the left side, are supervised learning. One is showing regression, the other one is showing classification. So you can see that in the case of regression, in this case, we have a two-dimensional regression problem, right? So we have an input on the x-axis, we have a y, and we're trying to predict y using, we're predicting y using x. And the prediction is going to be a line, right? Most practical applications, we don't just have two dimensions of data, we have many dimensions of data, so it's hard to visualize it the way that you do on this plot. Classification is similar, but we're not trying to predict a number. We're trying to predict categories. So if you look at the plot in the middle, you can kind of see that some of them are squares, some of them are crosses, and if you could just fit a line right through the middle, you'd be able to distinguish the squares from the crosses, right? That's an example of classification. And it's supervised because we know what's a square, we know what's a cross, right? If we try to separate the two, sometimes we're going to be right, sometimes we're going to be wrong, and we'll know when we're right and when we're wrong. The visual, the last visual on the right side, is an example of clustering. In this case, you kind of look at that and you see, okay, we have some points that are, they should be red, some points should be yellow, some points should be blue. It looks like they kind of divide into these three clusters, but we don't have in the data, we don't have any information that says that's the correct answer. Your clusters are good, right? We look at this data and it looks pretty obvious that we have three clusters. Most of the time when you have multidimensional data, you can't just look at it and say, well, okay, it's pretty obvious. So it's a very complicated problem and there is no way for us to really evaluate our answer. We can basically just build clusters and try our best at judging them. So here's an example of regression. Right? We have some vocabulary to go over. So first we have data. Right? Our data is going to be comprised of some inputs and outputs. Sometimes the inputs are referred to as features. The output is referred to as a target. Right? And in this case, the target is income because it's a number. We call this a regression problem. Right? And the process of building a model from that is going to take the inputs and try to predict the output is called learning. When we evaluate regression models, we want to see how close do the predictions come to the observations. What we mean by observations is, like we said in supervised learning, we know the answers, right? We know what the actual value is. That's what we call the observations. And the model is going to give us a prediction. So we can just ask, how close are the predictions coming to the actual things that they're trying to predict? And so we have different metrics. I would point you more specifically maybe to the second row in this table. What we call the RMSE, the root mean squared, is one of the most common metrics for evaluating a regression model. Another one is R, correlation. Right? So a high correlation means that our predictions are very highly correlated with the observations. So we talked about supervised learning. Now let's talk about, we talked about supervised learning in regression. Now we have supervised learning classification. The only thing that changes is our last column in the data. Right? Before it was a number, now it's a category. In this case, it says, should we purchase or should we not purchase? Right? So this is a model that's going to look at whether someone is married or not. It's going to look at somebody's favorite color. It's going to look at somebody's income, and it's going to try to predict, based on those three inputs, if someone is going to make a purchase or not make a purchase. Right? Once again, it's supervised because we have historical data of people's marital status, favorite color, and income, and we know in the past if they purchased or not. Based on that data, we want to predict in the future if we have someone in that situation, what do we predict about purchasing or not purchasing? Okay. Another thing I would point out here is notice that we have two data sets. right? One is called training set, another one is called testing set. I'll talk more about that in just a minute. Okay, classification and regression are both supervised learning algorithms, but the way that they are evaluated is slightly different, right? In regression, we have what I mentioned was the root mean squared as one of the most common evaluation metrics. In classification, we can look at other things such as accuracy, precision, and recall. Now, it's probably more useful to look at the table that you see on the left side, right? So when we predict in classification, we could predict for multiple categories, but the more common scenario is we have to predict for 2 categories. Is it a yes? Is it a no? Is it someone has cancer or someone doesn't have cancer? Someone is going to purchase or not purchase, right? So a lot of problems are just 2-category classification problems. And in that case, our job is really easy. We can say if someone is really in the true category and the model predicts a true category, then that's a good prediction. If someone is in the false category and the model predicts a false category, that's a good prediction, right? So what you have in the diagonals of the table, those are good predictions. What you have off the diagonals, the false positives and false negatives, those are bad predictions, right? Now, the very, very important thing to remember is that we can tune our models to some extent. We can try to reduce as much as possible the false negatives, for example, but it's going to be at the expense of false positives. It's practically impossible to reduce your false negatives and false positives at the same time. Usually, we have some trade-offs that we do when we have classification models. We'll see more about that when we run our experiment, right? But let's examine visually the last one, clustering. Right, so here's the data. If you look at it, some of you might think, okay, there's 2 clusters. Some of you might think we have 6 clusters. Some of you might think we don't really have clusters, right? Nobody would be right, nobody would be wrong. In clustering, we just don't know, right? How many clusters we have partly depends on the data, the structure of the data. We want to find some kind of structure in the data, but there is some amount of subjectivity involved when making these decisions. Right? So here's an example of 2 clusters and 6 clusters, right? Both of them look reasonable, and it depends on sort of what we choose, right? If we have 2 clusters, we can agree that maybe we have a more simple model, right? Simplicity is usually good. It means we have to spend less time trying to understand it. If we choose 6 clusters, we have more details. We have a more complex model, and we have to try to understand really if we look at the data points on the left and the data points on the right, right? They're very different from each other, but if we just look at the ones on the left, we have 3 different clusters on the left side. What is the difference between the 3 on the left side or the 3 on the right side, right? We have more to do to try to examine these clusters, right? And somebody could say there are 4, right? We could have like something in between. So subjectivity means there isn't really a true answer out there. We can't really say there is exactly 2, 6, or 4. We have to provide some input. Based on that, the algorithm is going to run and give us some output. And we're never going to really be completely certain about whether we're doing the right job or not. 2 common examples of unsupervised learning algorithms are called clustering, the one that we were just looking at, and principal component analysis. Principal component analysis, if you will, is what we call clustering for the columns in our data, right? So when we talk about clustering, like the example here, each point that you see on the scatter plot can be thought of as a row of the data. So when you say there are blue points and red points, you're basically taking the rows of your data and dividing it into a bunch of blue rows and a bunch of red rows. You're labeling the rows of the data. In PCA, principal component analysis, we try to find groups of the columns in the data. So we say there are lots of columns in the data. Some of them are related to each other. If you have something about weight and height, there might be some kind of strong relationship between weight and height. Kids have low weight and low height. Adults have higher weight and higher height. Right? So that relationship means there is a certain amount of redundancy in having both of the columns. And PCA tries to reduce that redundancy. Okay, so we're going to go back to our Azure ML Studio, and we're going to try to build two different models. What I have here is I have a visualization of the data, so you can kind of see what the end product is supposed to look like. We already have the German data. We have edit metadata. You can go back and you can delete the summarize data module. And we're going to try to build two models. One is called linear regression. You can see that on the left. One is called two-class logistic regression. You can see that on the right. And we're going to train both of these models. We're going to make predictions and evaluate them. So the instructions are right here. And once again, I'm going to give you maybe about 2-3 minutes to try to do it on your own. I know it's not a lot of time. Usually I should be giving you more time, but we just don't have that much time. So I'll just give you a minute or two to just get started, and then I'll jump in and do the exercise with you. So we're back here in the Azure ML Studio, and the first thing I'm going to do is I'm going to delete the summarize data module, and I'm going to go and find a regression module. So you can just type regression. You're going to see that we have multiple kinds of regression. The one that I want is called linear regression. So I'm going to drag and drop it here. Then I'm going to look for something called train data. Train model, sorry, not train data. Train model. I'm going to drag and drop that in here. Then I'm going to look for another one called score model. Drag and drop it in here. And one called evaluate model. And once again, drag and drop it in here. Now, we're going to build two different models. So we're going to have to do this twice. And the easiest thing to do would be to select all three of these. And you can copy and paste it again. So Control-C, Control-V. And now you have the same modules copied over. And you can drag them to the left side, to the right side of the screen. Notice we have these red exclamation marks. That's a sign that something is missing. Right? We need more to provide more input. And the other thing is I need to also pick a, I think we chose logistic regression, right? So I'm going to search for logistic, and notice we have a two-class logistic regression. That's when your logistic regression is just trying to predict between two classes. And we have a multi-class logistic regression if there are more than two categories that we're trying to predict. So I'm going to grab the two-class logistic regression and drop it in here. I'm going to scroll up. And there's that. Okay, now that we have our models, or now that we have our modules, right? Each one of these boxes is called a module. We need to figure out what connects to what, right? To some extent, we can use some of the helper, some of the help that we get when we hold our mouse over these buttons. Right? So I can see that there is a untrained model that shows up when I hold my mouse over the first circle on train model. Right? So train model is expecting a model there. And I have a model, it's called linear regression. So I'm going to go and connect the two together. Then I'm going to go to the box on the right, and notice this one says data set. So it's expecting some data. Right? That makes sense. If you're trying to build a model, you need to specify what model, and then you need to specify the data that you want to build a model with. Well, I'm going to go and fetch that from edit metadata. So you connect that. So I still see a red box, right? So something else is missing. So we provided the data, we provided the model. What it doesn't know is what it's predicting, right? And so we need to specify that. And I'm going to click on train model. And notice when you click on it, there is a column selector. If you come here, it says select a single column. That single column is the column that we're trying to predict. And because we chose linear regression, we need to predict a column that's an amount, right? A number. So we're going to select credit amount, hit the arrow there. It's going to go to the right. And then you have to make sure that you click on the check mark. And now the red exclamation mark is gone. Okay. So that's how we progressively go from building a model to the next step, which is to run predictions. So train model is going to give us a model. Now we want to go and run predictions on that model. So let's see if what score expects from us. The first little box there says you need to give me a trained model. Right? I want to make predictions. If you want me to make predictions, I need the data that I want to predict, and I need a model to predict with. So the model is just going to come straight from trained model. There is that. The data that we choose in this case is going to be the same data, right? The same data that we used for building a model is now going to be used to make predictions. So that's what score is doing. And the last thing for us to do is to run evaluate model, right? So it says, give me a scored data set, and I will evaluate the predictions. So connect those, and you're done. We're going to go to the right side and do exactly that with the other model. So in this case, we have a two-class logistic regression. I'm going to connect that to train model. I'm going to connect the original data to train model as well. And I need to specify the column that we are predicting. For logistic regression, for a two-class logistic regression, we need to provide it with a binary column like credit risk. Here's someone who's a credit risk and someone who's not. So we select credit risk, we hit the check mark, connect that to score. Once again, we get the original data. So we build a model with the original data, and we score the same data with the model we built. And lastly, we're going to connect score to evaluate model. And now we have everything connected to everything else. I'm going to hit run. And this shouldn't take very long. It should just be just a minute or so. And it's going to go and build the two models that we wanted to build. As it's happening, we should see it progressing. When you see the little clock, it means we haven't gotten in there. We haven't gotten to that point yet. As soon as it finishes running a particular module, you're going to see an arrow, and it's going to move on to the next one and the next one. So while this is running, just kind of go back and take your time and finish your own experiment if you haven't had the time to do it yet. And then we can examine the results together. Okay, so I finished running the experiment. And we started with the original data. With edit metadata, we changed the column names. That's all we did. And then we came here and we built two models. Both of them are supervised learning models. That means that they make predictions. One of them predicts credit amount. It's a number. We call it a regression problem. The other one, even though it's called logistic regression, it's not a regression problem. It's a classification model. It is trying to predict credit risk. So some of the terminology there might be confusing, but linear regression is a regression algorithm. Logistic regression is a classification algorithm. So let's take a look at what they return. We're going to run trained models. We're going to right-click on it, and we're going to try to visualize it. And so it's returning basically a bunch of information about the model, including what we call the feature weights. Right? So these are basically going to go into creating an equation, and that equation is going to be used to make predictions. You can't see the actual equation here, but you can see the numbers that go into populating the equation. Right? The higher the number is here, the bigger of an impact the particular column has on the prediction. Okay? So a regression is ultimately some kind of equation, some kind of linear equation that's going to run a prediction for us. And you can see the coefficients in this case. Let's take a look at what score model is showing. So right-click on score models, go to scored data set, and try to visualize it. And what we should see is the original data. Right? We can see the original data back. But if you scroll all the way to the right, now we have a prediction. Right? So this is what we have as our credit risk. This is what we call our observation. Sorry, we're looking at credit amount. So the regression is trying to predict credit amount, which is right here. So in the data, we have somebody whose credit amount was $1,169. Our model predicted that their credit amount would be $547. Okay. So score model is going to add a new column to the data that contains our predictions. This is something that we can compare to the actual observations shown in the credit amount column. Because of this, we call this a supervised learning algorithm, right? We have predictions, we have the observations, and we can go and evaluate our results. Just from here, we can do some basic evaluations. We can see that for the whole data, the average credit amount is something close to $3,200. We can compare that to the average predictions. The average predictions are also very close, pretty much on spot, right? So some of this is just the structure of the model. The way that these predictions come about is not something that we're going to really talk about today, but we have a working model. Now, to really evaluate the model, we don't want to be going down the rows individually looking at predictions versus the observations, right? So that's what we have the evaluate model for. We're going to go to evaluate model, click on it, do a right click, evaluation results, and visualize. And it says, here is the root mean squared. Right? So root mean squared is one of the most common evaluation metrics for regression. And what that number represents is basically the average deviation of the prediction from the observation. Right? On average, our predictions are off by about this much. Okay, that seems like a very high number, so maybe our predictions need to be better. Maybe we should work on building better models. But that's what we have. We can also look at a histogram of our errors. The error is the difference between the prediction and the observations. Right? And this histogram kind of shows us that in most of the cases, we are off by a very small amount. But there are some cases where the error rate tends to be pretty high. So that's regression. Let's go to the right side and take a look at what classification does. So logistic regression is a classification model that's very similar to regression in the sense that it also returns some kind of equation. And the equation is represented here by these weights. Okay. In statistics, we tend to spend a lot of time trying to understand and interpret this number. But in this case, what we're doing is we're just saying whatever that equation is, just use it to run predictions, and score model is going to do that. It's going to take that trained model, it's going to plug it into that equation, and it's going to give us the following two columns. In the regression example, we got one column. In the classification example, we're going to get two columns. Here's the original credit risk. That's what we're trying to predict. Here is the scored labels. It's saying somebody was low risk. That's why we have a 1 there. And we predicted low risk. So that's a good prediction. Somebody was high risk, and we predicted high risk. That's a good prediction. We can scroll down and see that the majority of cases are pretty good, but here is an error. Here is somebody who was high risk, and we predicted that they were low risk. The last column that you see here is the probability of being high risk. Right? So notice that when we're predicting 1, that's a low risk, and the probability is really low. When we predicted 2, the probability is much higher. Right? So we have both the probability and the actual label that we predicted. There is some other information shown in here, but we can just go and take a look at evaluation model. And what evaluation model does is it just gives us a summary of what's going on with the model. The first summary that we get is this plot. It's called an ROC plot. And essentially what you want to do here is you want to get a curve that as much as possible pulls toward the corner of the plot there. Right? So the more your plot is going to be vertically going up and then horizontally over, the better of a model you have. Right? The more the line is going to be close to the 45-degree line, the worse of a model you have. Once you're on the 45-degree line, your predictions are worthless. You may as well just toss a coin. Right? So that's one visual evaluation metric. Here's another evaluation metric. Right? So here's true positives. These are good predictions. Here are true negatives. These are also good predictions. These two are the bad predictions. These are our errors. These are cases where the model was wrong. Right? And we have a threshold. Right? So when we predict with the model, it gives us actual predictions, but we can change those predictions. We can say, I am not confident that if your probability is more than 0.5, you should be predicted as high risk. I'm going to raise the bar. I'm going to say, if there is more than a 71% probability that you are high risk, then you should be labeled as high risk. Notice that as you change the threshold, true positives, false negatives, false positives, true negatives, all of those numbers change. Right? We don't want to be at the extreme of the thresholds, right? Because then the model is making a very simple and naive prediction. We want to be somewhere in the middle, but there is some subjectivity as to exactly where we want to be. We need to decide, do we care more about reducing false positives, or do we care more about reducing false negatives? Right? And depending on the business situation, depending on the prediction that we're doing, one might be more important or more costly than another. Right? So there is some amount of decision on our part or input on our part before we settle on the exact threshold that we're comfortable with. Okay. So let's go back to our slides. Right. So we saw a little bit of the mechanics of using Azure ML. Right. And we saw an example of a supervised learning algorithm. I lost my clicker. Okay, well, oh, there it is. All right, so we saw an example of a supervised learning algorithm. We saw an example of one that is doing regression, predicting a number. We saw an example of one that's doing classification, predicting a label. Right? Now we're going to talk about some concepts behind machine learning. Right? And these are extremely important. These are if you will, like best practices for doing machine learning. And so these are some of the terminologies that we're going to learn in the next, let's say, 20 minutes or so. We're going to see what it means to fit a model. Right? We already sort of know that. So what we just did was fit two models. Right? We called it training. Now I'm using a slightly different term, fitting. Both of them are pretty common. Right? We saw an example of predicting. That's also called scoring. Right? So again, some vocabulary there just because people call the same thing by different names sometimes. So if you hear the word predicting, think scoring, right? And as we saw in Azure ML, the module's name is score model. We have a train model and we have a score model. Then we're going to see what it means to do some pre-processing, right? So data that we use, the raw data that we use for modeling is almost never ready to fit into or to be given to a machine learning algorithm. We have to process that data. We have to clean that data. We have to sometimes aggregate that data to get it ready for modeling. And the last thing that we're going to see, probably the most important thing to take away from today, is the fact that we need to split the data. So we're going to split the data into a training set and a test set. And I'm going to try to provide an example of why we do that. Okay. So here's a very common workflow when we do machine learning. Almost any time we build a model, some kind of process like this is going on. We're going to start by defining an objective, right? We don't start with a model. We don't go and say, I want to build a regression model. Give me some data, right? We say, what are you trying to predict? What is the business use case? What is the objective, right? And based on that, we have to decide what is the appropriate model. Right? If we're trying to predict a number, we can choose a regression model. There are other possibilities, right? There are multiple models for doing classification, multiple models for doing regression, and there are also different models for doing unsupervised learning algorithms, but we always start with the business objective, right? What kind of question are we trying to answer? Then we ask, what kind of data do we have, right? So let's go take a look at the data. Let's look at some summary statistics. Let's see if we have missing data. Let's see if we have extreme values, what we call outliers in statistics, right? And what do we have to do to clean the data? This is something that I talk more about tomorrow in the section on choosing a machine learning algorithm. But there is a lot of work involved in this process. You might argue, and this is definitely for me, I would say that's probably a reasonable number, about 80% of the time when we build models, about 80% of the time goes into just cleaning the data, processing the data, doing all of our due diligence to make sure that the data is ready for modeling. Right? So that all falls into this idea of pre-processing. First, we understand the data, we look at visualizations and such, and then we do everything that we have to do to get the data ready for modeling. So, common pre-processing tasks involve aggregating the data, right? Sometimes we have data that's very granular. Maybe every row of the data represents a credit card transaction, and we're trying to build a model that is more trying to look at different customers, right? So if you think of a clustering algorithm, and you have a data set that shows people's credit card transactions, and you want to divide your customers into, here is a bunch of customers who spend a lot of money, and here is a bunch of customers who don't spend a lot of money. Here's customers who go and spend money buying a lot of groceries with their credit card, and here's customers who buy mostly luxury items, right? So that's an example of clustering, but notice that I'm talking about customers, right? So if you're trying to build clusters on customers, but the original data is every row is a swipe of the credit card, first we have to aggregate the data on a customer level. So that's an example of aggregating. Sometimes we take samples, right? Especially if we have a lot of data and we want to just try and experiment things. We don't want to wait around. We take a sample of the data. We kind of work with the sample for a while to get a good sense of the data. Sometimes we have to reshape the data. Missing values are extremely common. Any data that you look at is bound to have some missing values somewhere, and we need to be asking, we need to wonder what we need, what we have to do with the missing values, right? Some models don't care. If you have missing values, they still work. Some models are very sensitive to missing values. We should also be asking, are there missing values for a particular reason, right? If it's more common to have missing values for some data points than other data points, that might be a problem. Okay, same thing with outliers, right? Outliers are values that are extremely high. If you're looking at data that represents, once again, credit card transactions, an outlier could be something like a negative credit card transaction. If it's negative, it could be a return, right? People buy things and return them. It's not necessarily an extreme value in the sense that it's negative, but it's not very high. But it's extreme in the sense that it might not be relevant to the analysis that we do. Lastly, feature creation and feature selection. So the features are the inputs to the models, right? And we have to do a lot of work to clean them up. Sometimes we have to do transformations. Again, these are topics that depend on the model that we choose. Okay. Common featureization techniques include things like normalization. We might have data that has different columns. Some of the columns are going to have a much larger scale. Some of the columns are going to be very limited. If you think about data, for example, where one column is denominated in US dollars, showing amounts, another column is using, I don't know, Mexican pesos, right? Well, the two are not on the same scale. Something in US dollars is going to be much smaller value, and the corresponding Mexican peso is going to be on a much larger scale. So an example of pre-processing in this case is we put both of them on the same scale. Right? We could take everything and convert it into US dollars. That's one example of rescaling. We could also do some automatic rescaling using things like normalization. Binning or bucketing is also a very common technique. We could have numeric columns, and we can say, I don't want to deal with numeric columns, so let's just bin it. Let's just take everything between 1 and 10 and call it one category, everything between 10 and 20 and call it another category. And sometimes feature creation is just the process of just doing certain automatic calculations, and it's really probably the most intensive work that we do in pre-processing, just creating useful features. Right? When we're done, we come here. Right? Now we have data. It's not just the raw data, it's data that's ready for modeling. We took care of our missing values. We took care of, we basically did our due diligence on the data. And we think that we have clean data, and now we're ready to go into modeling. So our data is at the top, and the first thing that we do with the data, something that we haven't done yet in Azure ML, but we're going to do it in the next exercise, is to split the data into training and testing. When I say training, remember the train model module in Azure ML. Training means building models. Here's some data, here's an algorithm, please go and build a model. Testing is going to be used to make predictions. Right? So what we're doing is we're basically dividing our data into two sections. We're saying use some of the data, but not all of it. Use some of the data to build a model, but set aside some of the data for predictions. Right. When we have a model, we then go and run predictions on it. So notice that if you look at testing data, there is an arrow going down from testing data right into score model. Right. So we build the model, and then we take the testing data and we run predictions on it. When we evaluate our predictions, we evaluate them on how good the predictions are on the testing data, not on the training data. Okay, so that's the general idea here for splitting. I want to give you just maybe an analogy that would help you kind of see why this is important. Let's say that you're going to take a test, and this is sometimes not a very good analogy. Think of like a driving test, right? So you're going to get a driver's license. And some of it involves driving, but some of it involves like an exam. You have to take an exam to see if you know the laws. Nobody ever studies for that test before the test. You get a practice test in most places. You get a practice test, you take it home, and you study quickly for maybe like 4 hours, and then the next day you go and take the exam. Right? So imagine that sort of situation. Imagine you have something that you know nothing about. Somebody gives you a practice test and says, here, take this home, go learn using the practice test. Tomorrow, there is an exam, you're going to come back and take the exam. And let's say that what you're interested in is maybe you're a little bit worried. You want to know how well you're going to do tomorrow. Right? So you're not just interested in learning, you're trying to predict your score tomorrow in the exam. So if you are a machine learning expert, I guess, this is what you're going to do. You're going to say, I'm going to learn from the practice exam, but I'm not going to use all of the practice exam for learning. I'm going to set aside maybe just a small section of the practice exam, and then I'm going to use, so let's say we have 100 questions. I'm going to use 80 questions to learn, right? And I'm going to learn the laws, and I'm going to try to just do a good job. And then the other 20 questions that I set aside, I'm going to test myself. Right? So they're not going to be used for learning. I'm going to take them. I'm going to pretend it's an exam. And whatever score I get on the 20 that I set aside, I predict that's the score I'm going to get tomorrow when I take the exam. Right? The reason we're doing this is we want to be careful. We don't want to just learn. We don't want to take all the questions that we took for learning and test ourselves on that. Because if we do that, we're going to be overconfident, right? If you use the same questions that you were using for learning to test yourself, in a way, you're a little bit like, it's a little bit like cheating, right? You're overconfident. You already know those questions. Maybe you memorize the questions. Maybe you didn't learn anything. You just memorize the questions. And if you test yourself, you're going to get 100%. That doesn't mean you're going to get 100% tomorrow when you take the exam, right? So to be fair, we can't test ourselves on the same material that we use for learning. We need to divide them into something that we use for learning and something that we use for testing. Right? And that's exactly what we do in machine learning in the prior slide. We use most of the data for learning, but some of it is set aside so that we can run predictions, examine those predictions, and if they're really good, the predictions should not only be good on the training data, we don't care about those predictions, the predictions should really be good on the test data because that data was not used for learning. Okay, so what I just described is shown graphically in this visual. And this is probably the most important machine learning concept that we'll talk about today. So you can see on the vertical direction, we have some measure of error. Right? It doesn't matter if we're talking about regression or classification. We have some kind of supervised learning algorithm, and we have a measure of error. On the horizontal, we have something about model complexity. Right? Some models are really easy. Some models are really complicated. We'll see some examples in practice when we go back to the studio. Right? And here's what's going to happen. If we have a bad model, there's two ways that we can have a bad model. Some models are just going to be very naive. They're just not going to be very complex. They're going to look at the data. They're not going to pick up too many patterns. They're just not very good models. In that case, we're going to do a poor job when we look at the error on the training data and the error on the test data. Right? And so we're going to notice that the error is high, and we're going to be tempted to build more complex models. Right? The problem is if we look at the blue line, if we use that as our measure of how well we're doing, then we're going to notice that as we build more and more complex models, the error is going down and we're feeling overconfident, right? Overconfident because this is similar to the situation where you have your practice test, you memorize all the answers, you don't do any learning, you just memorize the answers and you feel like you take the exam again, you don't look at the red line, you don't test yourself on other questions, you test yourself on the same questions that you use for learning and you feel like 100% I'm all set for tomorrow. So what we should be doing is we should be examining the red line. And the red line says, actually, there is a point beyond which models get too complex and you don't do a good job of generalizing. Right? So when you use the testing data, the models are doing a bad job predicting on the testing data. Right? So we want to be somewhere in the middle. And those are the models that do the best of generalizing. Okay? So the situation on the left is called underfitting. The situation on the right is called overfitting. Overfitting is a term that you hear very often, and you can see that described here. Okay, so we're going to go back to our lab. We have about 40 minutes or so. And we're going to take probably like the next 10, 12, 15 minutes on this lab. So once again, just kind of take a look at what we have here. We have basically two models we're going to be working with. And in the last exercise, we learned how we can build a model using trained data. We learned how we can score a model with the score model module. But we didn't do the important thing. We didn't split the data into training and test set. So in this exercise, we're going to do that. We're going to split the data into training and test set, and then we're going to build two classification models. Right. Not regression and classification, two classification models. One is a boosted decision tree. The other one is a two-class support vector machine. You can see the boosted decision tree on the left. You can see the two-class support vector machine on the right. So there's a lot of instructions here. I'm going to leave that up. I'll give you about 5 minutes. Try to kind of do it on your own, and then we'll work on it together. And the first thing I'm going to do is I want to get rid of everything after edit metadata. So we build a bunch of models, and we're going to redo it now. We're going to try different models this time. And we're also going to split the data before we do any modeling this time. So let me get rid of both of those. And we're kind of back to square one. Right? So there is our data. We rename the columns. And now we're going to add some pieces to it. We start with the splitting part. So if you just type split, there is split data. Right? And I'm going to bring that in. Notice what split data does. So first we carry the data over. We give it to split data. And split data is going to return two, not one, but two data sets. Hold your mouse over the first one. It's called data set 1. The other one is called data set 2. Right? The data set on the left is going to be the training data. The data set on the right is going to be the test data. Okay. Now, I'm going to choose a model. The model is going to be a two-class boosted decision tree. Right? So that's the first model. Drag and drop it in here. And we're going to build the model only on the training data. So I'm going to take train model and drag and drop it in here. Okay. And what I'm going to do now is I'm going to go to this left data set. That's the training data, and that's going to feed into here. I'm going to take the model and pass that also to the training data. And finally, I have to select the target. So the column that I am predicting is called credit risk. So there is credit risk. And if we do all three of those, now the exclamation mark disappears. Okay. So that's the training part. Really the big piece that we've added, the big difference compared to the last homework exercise, is now we have split data. We drag only the data set on the left side into train model, and we're going to go and drag in a score model module. And what we're going to do with score model is we're going to say, here is the training data, here's the trained model. So we have a model that I want you to use for prediction, but instead of predicting on the original data, I'm going to come here and drag the data from the right side down into score. Right? So I'm saying you're going to build a model on this data. That's what that arrow is doing. But you're going to score the model on this data. That's the test data. Okay. The last thing is for me to evaluate it. So evaluate model. And I'm going to drag that into here. Right. So we can evaluate two models at the same time. For now, I only have one of them. So let me go ahead and build the other model. But before I do that, maybe I'll give you another just 1 minute or so to come up to speed on this. So just take a minute, see if you can do this. You should not see any red exclamation marks. And if you want, you can go ahead and run the model, even though we don't have it completed. We don't have the experiment completed. We can run this part of the experiment for now. So it finished running. I can go down to evaluation results, and I can try to visualize this. So it's a classification model. It's going to show me, for a two-class classification model, it's going to show me this ROC plot. Right? I don't know yet if this is a good model or not, right? But we can build another model and try to do some comparisons. I can come down here and look at some metrics. I can see that the error rate is actually pretty high, right? So we have a lot of cases of false positives and false negatives, right? And we can play around with the threshold, right? But we'll never be able to reduce the false positives and false negatives at the same time. Notice that when you decrease your false positives, your false negatives tend to go up. When you decrease your false negatives, your false positives tend to go up. This is sort of like a law of nature, if you will. So now let's move to the left, to the right side, and we're going to redo this, but with a new model. This model is going to be called two-class support vector machine, and so there is the model. Both of these models, both the two-class boosted tree model and the two-class support vector machine, are kind of complex models. The algorithm that is behind it is sort of a complex algorithm. There is a lot of stuff happening. We'll talk a little bit more about that sort of thing tomorrow. For now, we just want to implement these models in practice and see how they work. So once again, we're going to look for train model. We're going to look for score model, and we're going to drag both of those in. But there is another thing that we're going to do. What we're going to do for this model is we're going to do some feature engineering that we didn't do with the tree model. Tree models tend to be pretty simple. They don't require too much feature engineering. Right? They just try to split the data based on some kind of threshold. And because of that, they don't really care about the scale of the data. If two columns are on a different scale, for the tree, that's not important. For something like a support vector machine or a regression model, that's kind of a big deal, right? So in the case of support vector machine, we're going to have to do some featureization. Now, notice that if you click on the two-class support vector machine, there is already featureization built into it, right? So there are some algorithms, such as support vector machine on Azure ML, that automatically try to do some featureization, right? Try to do some feature engineering for us. I'm going to uncheck that, and I'm going to do it slightly differently. I'm going to bring in something called normalize data. Right, so there is normalized data, and I'm going to bring it in twice. Okay, so it's starting to look a little bit busy here, but hopefully not too bad. Right. And so the reason I want to do this twice is we split the data into a training and a test set. If we want to build a model, we need to do our feature engineering on the training data. But if we want to run predictions, we have to do the same feature engineering on the test data as well. Right? So that's one of the drawbacks of doing a lot of feature engineering is whatever we do to the data when we train it, we have to do it to the data when we run predictions on it too. Otherwise, our predictions are not going to be accurate. Okay, so we normalize the data both for training and testing. Now, here is the data for training. I'm going to pass that to the train model. Here is the actual model. I'm also going to pass that to the train model. Right? And now we have data that we can train. I just need to select the column that we're actually predicting, which is credit risk. Score is going to be the same way. So the data on the left side is my training data. The data on the right side is my data that I'm going to score. That's the test data. And I pass the trained model to the score model module, and there we have our scoring. The last thing we have to do is connect score to evaluate. So both of these models are predicting the same thing. They're both predicting credit risk. One is a boosted decision tree. The other one is a support vector machine. And we can feed both of them to the same evaluate model module so that we can compare the two predictions. So I can run this now, and it should start running the second model for me. Now, everything that you learn in here, you're learning it through this visual interface. We're using Azure ML, we're dragging and dropping things. But if you're doing this programmatically, if you're using R or Python to do your machine learning, it's exactly the same concepts. Right? We would use programming, but we would still split the data, we would still do our featureization, we would do everything that we're doing here, but using one of those programming languages. Right? Okay. So we have our model, the evaluation just finished. Let's take a look at what the models look like. Let's see if we can take a look at what normalized data is doing. So I'm going to go to transform data set, and I'm going to try to visualize it. Okay. And oh, there is actually something that I forgot to do. Right? But I'll do that in just a second. Notice that duration in months, credit amount, these numeric columns, they look a little bit strange. They're not the original columns anymore. Credit amount used to be a pretty high value. Now if you look at it, the average is 0. The median is very close to 0. Right? So something happened to that column. Some kind of rescaling has happened. Not just to credit amount, but to anything that is numeric. So here's another one, and once again you can see the average is 0. So that's an example of a rescaling transformation. Okay. Now, what I forgot to do in the data is when we normalize the data, we have to specify what we're normalizing. So I'm going to go to column selector, and I'm going to say, yes, you want to include all of the numeric columns. but I don't want to include credit risk. Right? So credit risk is also a numeric column, but that's a 0, 1 numeric column. It's what we're trying to predict, and I'm going to leave it out of the normalize data algorithm. The other thing I'm going to do is there are different options for normalizing. So the one that we were just looking at where the average is 0, that's called z-score normalization. We can choose something else, and in our case, we're going to use this kind of normalization. Since we did it with the training data, we also have to do it with the test data. So let me do that real quick. So include, oh, I have to change that to exclude, right? So include all numeric columns, exclude the column called credit risk. Right? I think I forgot to choose exclude in the other one, and then change the transformation there. So I'm going to fix this real quick. There is an exclude credit risk, and that's it. So we take the data, we normalize the numeric columns except for credit risk. We don't need to normalize credit risk. Then we train the data. Then we evaluate our models. And I have to rerun this since I made changes to the normalized data module. And then we can compare the two models. Okay, so we have, I retrained the two models, rescored, and we have the evaluation. We can go back to look at normalized data just to make sure that everything happened correctly. So if we look at something like credit amount, right, it looks a little bit different now. It's a different kind of normalization. Right? And if we go and look at credit risk, nothing happened there. It's still zeros and ones as it was before. Right? So all of the numeric columns were normalized except for credit risk. And we can kind of see what that normalization looks like. Right? And we can play with different options for normalization. Same thing with the test data. Then we train our model. We can take a look at what a two-class support vector machine model looks like, what kind of information is displayed to us. And whenever you see something like this, where you have features and you have weights, you can know that it's some kind of regression-like algorithm. Right? So a support vector machine is very similar to a regression algorithm, but there is more that's happening behind the scenes, and the optimization is sometimes a little different. Right? But we get some kind of equation out of it, and this is some manifestation of that equation. We can look at score model to see if our predictions look good. Right? So we're trying to predict credit risk. Here is a case where somebody was low risk and we predicted low risk. Here is a case where somebody was low risk and we predicted high risk. We can see from the probability why this one is a 1 and why the other one is a 2. That probability is really low there, but the probability is much higher here. Right? So we can see our predictions. We don't know how close they are to the actual credit risk of the individuals until we go down and look at the evaluate model. Right? So let's take a look at that. But before we look at the evaluate model, let's see if we can see the boosted decision tree. Right? So train model, visualize it, and let's see if it looks anything like a support vector machine. Right, so things are very different now. Notice that on the left side, we can see things that look like trees. So we know that a boosted decision tree is some kind of tree-based algorithm. We also notice that we don't have one tree, we have lots of trees. Right? So we can actually scroll down and more trees are going to show up. So we know that a boosted decision tree is not using a single tree to make predictions, it's building multiple trees. Models like this are called ensemble models. They're complicated models in the sense that they run the same algorithm over and over again to try to improve on the prediction. This is a good thing in the sense of being able to make better predictions. It's a bad thing in the sense that it's very hard to know what exactly the model is doing. We have lots of trees to look at. We don't really know how it's thinking. But we can look at one example of those trees. Right? So here's a tree. And I'm just going to zoom in a little bit. I'm going to scroll up to the top of the tree, zoom in some more, and this is what this tree is doing. It's basically looking at the status of the checking account as the first criteria. It's saying if the status of the checking account is less than 0.5, then split the data into these two groups. And basically keep splitting the data until we get to these blue circles. The blue circles are what we call terminal nodes. That's where a decision is made. So one decision is if the status of the checking account is less than 0.05, and if the status, and we're talking about different checking accounts, so one is A14, the other one is A13, right? So this is categorical data. Status of the checking account is categorical data. It's looking at one category, and then it's looking at another category, and it's saying, for this one, here's a decision. My prediction is 2. 2 means high risk, right? And so on. So this is going to keep going, and it's going to take the data and break it up into these complicated kind of tree-like structures, and at the end of the day, it's going to make a prediction. It's going to do this multiple times, and so we can see different trees. The trees don't look like each other at all, but ultimately it gives us a prediction. Right? Let's go and take a look at that prediction. Right, so we saw the prediction for the support vector machine. We saw that it looks like an equation. Now we have predictions that are made by the boosted tree. Right? Here's the actual credit riskiness, and here is the prediction. Here is a 1 and a 1, that's a good prediction. Here is a 1 and a 2, that's a bad prediction. And again, here's the probability that somebody is high risk. Okay, so we have both the actual labels that were predicted, and even better, we have the probabilities, so we can choose our own threshold for where we want to draw the line between low risk and high risk. Okay, the last thing we're going to do is just go and evaluate both of these models so that we can compare them. Right? Which model is better? Well, it's kind of hard to tell which model is better if you look at individual predictions, right? That's a lot of rows of data to look at. But we can come here. The model on the left in blue is the boosted decision tree. The model in red is the support vector machine. We can see that the lines are pretty close to each other. It looks like the blue line is slightly better at making predictions than the red one. So it looks like the boosted decision tree is slightly better than the support vector machine. The accuracy is one of those overall metrics we can look at. Accuracy is set at 73%, or 0.73, I shouldn't say percent, just 0.73 in this case. And for the other one, we get very similar accuracy, right? So sometimes we have a kind of a pretty tied results. Probably just looking at the blue line, I would guess, you know, if I were doing this, I would probably just take the boosted decision tree, right? Which model is better? Depends, right? If you only care about prediction, you could choose the boosted decision tree here. Tomorrow, in the topic of choosing a machine learning algorithm, we're going to see that that shouldn't be the only criteria, right? Which model is better also depends, for example, on where is the model going to be used. Is it going to be used in production? Does it have to make fast predictions? If the predictions have to be fast, we should maybe pick a model that makes fast predictions, even if they're slightly less accurate, right? So there are all kinds of considerations to take into account before we settle on a model. But we can see that we have two models. Both of them are doing an okay job of predicting. Both of them are pretty close to each other. They don't really they compete with each other, I guess you could say, in terms of predictive ability. Okay. So I'm going to go back to the next topic. I have about 10 minutes or so left, and we don't have too much left to cover. So just bear with me. I know it's already 5 o'clock, and I know you're probably eager to finish the day, but we don't have too much left of the day, right? The last thing we're going to talk about is just the topic of deploying a machine learning algorithm. This is something that we as data scientists, maybe 10 years ago, we were not very preoccupied with this. Now we very much are involved in this process, right? Even if it's not something that we are experts in, it's something that we should be asking and we should try to understand better. We should not just be preoccupied with what kind of models are we building and are they good models, are they making good predictions? We should be asking, how do you intend to use these models? Are they being used by an application? Are they being used to power a dashboard? Are they being used as a web app? Right? For all of these situations, different models might be better suited than not. So this is where we are. We're in the purple territory, right? We have a model. We examined a bunch of different models. We ended up choosing a model that seems to work well, and now we want to deploy it. When I say deploy it, another way of saying it is we want to consume the model. And consumption here means that we want to put the model in a production environment. Future data is going to be coming in, and we want to make predictions on that future data, right? We split the data into training and testing in the modeling phase because we want to make sure that our predictions are objective, right? But really, in practice, in a production environment, we don't care about making predictions on historical data. We care about making predictions on future data, right? So as data is coming in, we're going to score the data and we're going to run predictions on it. And then what we do with the predictions depends on the situation, right? So we get some results and we have to decide if we display them on a dashboard, if we summarize them and do something with them, if we visualize them, and so on. So that's pretty much the workflow of a data scientist. And things that come into consideration when we think about deploying models have everything to do with, is this something that has to scale? Is this something that has to be fast or responsive? Is it going to be part of a web application? Is it going to be part of a dashboard, right? And we're less concerned about, is this a good model? We already answered that question in the last phase, right? We examined different models. We found a good model, but we should also be wondering if this good model is well suited for production. Right? So here's a lab, and we're going to go back to our German credit data set. We're going to keep one of the models that we have, the boosted decision tree, and we're going to remove the one that's related to the support vector machine. Right? So that's step one. Let me just go back to the Azure ML Studio and do that. So you can select this, that, and that. all of those are related to the boosted decision tree, and you can remove that. Right? So that leaves us with remove the SVM, remove the support vector machine. That leaves us with the boosted decision tree, the training, and the scoring. Okay. So for deployment, this is what we're going to do. Now, in most situations, this is not an easy job to accomplish. Right? This is when the data scientist is basically reaching the limits of what they can do, and they would reach out to someone like a developer and say, hey, if you're trying to put this model into production as part of a web app, I don't know much about building web apps. I have a machine learning model. Can you help me? Can we work together to make this happen? In Azure ML, this is something that is really easy to do, right? None of that is going to be a problem. We can build models, but even better, we can actually deploy them immediately, right? And there are tiers that we can choose. So there is a pricing tier, and if your web app has to scale well, we can change the pricing tier. We can choose a web app that is going to respond well to more requests coming in from users, right? And so we're going to see how that works in practice. We're going to set up the model that we have as a web service, right? And we're going to deploy it, and we'll see if we can try to run a prediction on it. So what I'm going to do is I'm going to, first of all, I'm going to hit run. Right? We deleted a bunch of things, so we're going to click on run again and run the experiment. Make sure that nothing is missing. And now notice that this button, Predictive Web Service, has been enabled. So I'm going to click on that, and a couple of things are going to happen. Kind of pay attention to what's going on here. You notice that, first of all, we have two tabs. We have a training experiment. That's where we were so far. But now we also have a predictive experiment on the right side. So we have a new tab. And some of the things that changed is we have an input and an output. The input is a web service, a web input. The output is also a web output. Right? We'll see that in just a second, but we don't have the data, the original data. Instead, we provide an input. Notice that the training, let me zoom in on this one. Right? Notice that the train model has also disappeared. Right? So when we talk about a web service like this, we're not interested in modeling anymore. We have a model. We want to make predictions. And we want those predictions to be in a web service. Right? We want to provide input and get output for get the predicted output on the fly. Right? So there is no more training going on anymore, but we have scoring. Right? We want to predict, and we also have a model. Right? This is a trained model. That is, it's not just an algorithm. It's an algorithm that's been trained on the data, and it's ready to make predictions. Okay, so that's our web service. I'm going to run this just to make sure that it works, and then we can deploy it and see what happens. If at any time you want to go back to your modeling experiment, all you have to do is just click on the Training Experiment tab, and you can try another model, or you can change the way that you tune your model. Right? But we're fine with this. So I'm going to click on the Deploy Web Service button. And this model is going to be deployed as a web service immediately. Right? It's almost magical the way that it happens in Azure ML. Right? Without us having to know anything about creating web services, creating websites, we basically have a model that can immediately be put to use. Right? And what I'm going to do is I'm going to go and click on the test button, right? And it gives me a set of inputs. Okay. So what happened there is the original data had column names call1, call2, and so on. and now the inputs are the same way. You can try to come up with some reasonable inputs, right? But when you fill in the inputs, at the end of the day, you're going to click on the inputs, and based on those inputs, it's going to provide you with an output. Okay, so that's basically what the web service feature does. It's become a little bit more sophisticated recently. Notice that it's in preview, but there is a new web service experience. I'm going to click on this one instead because you can see it at a higher level. Right? So we have the ability to monitor our web service to see how many requests it's getting in and if they're being properly served. Here's the dashboard for monitoring. I haven't made any requests to this yet. Well, the one, I guess, but that's where we would look at that. I'm going to come here to configure. Notice there are some options to configure, and then there is a page for consume. This is a place where we can provide the key to the web service to applications so that they can hit the model. And there is also some example codes here, right? So if you're a C# developer, you can come here, you can copy this, and now you have a way for your application, your C# application, to communicate with the model. Same if you're Python or an R user. Here's, by the way, the input in R. So you can see something very similar to the input that we were presented with on the web page showing up here in R. So the model can be consumed from R itself using the R API. I'm going to go to the test page. This is the page where we could test an input and see if we get an output. Right? So the model is expecting all of these inputs. If we don't provide it with all of the inputs and we test it, notice that we get some output back. Notice that as part of the model, we rename the columns. So it's not surprising that when we get an output back, we can see the renamed columns. Right. Any cases that are numeric were automatically populated with a 1, and so those stay 1. Any case where the column was categorical, we need to specify the category or it's going to be treated as a missing value. Right. And if we scroll down, we can see scored labels and scored probabilities. It's not showing anything. That's not because it failed, it's just because we didn't provide enough inputs. Right? So we can go back and we can change the inputs. It would probably help for me to take a look at the data. Let me just go get the data and open it in Excel. And I'll just copy the data over from Excel into the web service. So I'm just going to say, oops. A11, I'm going to leave that as 1. A34, 1. Maybe change that. All right, so I'm just providing a set of inputs to this web service using more realistic set of inputs than just the numbers that are there. Almost finished. Oops. Okay, 1 is fine. All right, so let's take a look at this. We have A11 as the status of checking account. Again, what exactly that data represents is not important at this point. Duration is in months is set to 1 month. So somebody has had an account for just a month. We know information about their credit history, purpose. We know their credit amount, so we know that they have about $1,100 of debt. We know information about their saving, employment, and so on. And we have a model that can take in this information and make predictions, and we are calling that model via a web service. I'm going to hit test the response, and notice that when we come back, the model is predicting that this person is a low-risk individual, and it's also providing me with the probability of them being a low risk. Right? So we were not only able to build a model, we were able to create or generate a web service using Azure ML and immediately test the model for making predictions. So that's all I have. All right, so if you have questions, since we're out of time, just come to me afterward. Here's my information if you want to get in touch. And if you're interested in learning more about modeling, definitely come to the session tomorrow called Choosing a Machine Learning Algorithm. And thank you for your time.